In a lab in 1927, physicists fired single electrons at a barrier with two narrow slits cut into it, one at a time, with long gaps between each launch. There was no way for one electron to interact with another. And yet, when they checked the pattern building up on the detector behind the barrier, it looked exactly like the interference pattern you get when waves ripple through to openings in a pond and overlap on the other side. A single particle, launched alone, was somehow interfering with itself. That result has never stopped being strange, and it sits at the center of one of the oldest unsolved problems in physics. Almost a full century later, researchers still do not agree on what is actually happening inside that experiment, or what it tells us about the nature of reality itself. To understand why this bothers so many physicists, it helps to start with something familiar. Imagine tossing tennis balls at a wall with two slits cut into it, with a second wall behind it to catch whatever gets through. Some balls hit the first wall and bounce off. Others pass through one slit or the other and land on the back wall. If you mark where each ball lands, you get two clusters, roughly lined up behind each slit. That is exactly what classical intuition expects from anything made of solid. Particle-like matter now replace the tennis balls with water waves. Water passing through to slits does something completely different. Each slit becomes a new source of ripples, and those ripples spread out and overlap. Where two peaks arrive at the same point, they reinforce each other, producing a taller wave. Where a peak meets a trough, they cancel out, producing calm water. The result, if you could freeze the pattern, is a series of alternating bands, tall and calm and tall again, spreading out from the slits. This is called an interference pattern, and it is the unmistakable signature of wave behavior. Electrons should behave like the tennis balls. They have mass, they carry charge, and in every other everyday context, they act like discrete little particles. But when physicists sent them one at a time through a double-slit setup, the pattern that built up on the detector was not two clusters. It was bands of alternating high and low probability, an interference pattern, the same kind of pattern water makes. Somehow, a single electron, with nothing else around to interfere with, was behaving like a wave spread across both slits at once. The obvious next question is simple. Which slit did the electron actually go through? So researchers added a detector at each slit, a way to check which path the electron actually took. And this is where the experiment turns from strange to genuinely unsettling. The moment you measure which slit the electron passes through, the interference pattern disappears. The electrons start landing in two simple clusters, exactly like the tennis balls. Just by looking, by gathering the information about which path was taken, the wave behavior vanishes and particle behavior takes over. Nothing about the electrons, mass, charge, or speed changed. The only thing that changed was whether a piece of information, which path was taken, existed anywhere in the universe. That single fact, whether that information exists, determines whether the electron behaves like a wave or a particle. This is often called the observer effect, though the word observer is misleading, since it has nothing to do with consciousness or a person looking at a screen. What matters is whether the environment now contains a physical record of which path was taken. A detector counts. A camera counts. Even a single stray photon that could, in principle, carry that information away counts. This experiment has been repeated with atoms, with molecules, and even with clusters of dozens of carbon atoms bound into soccer ball-shaped structures called Buckminster, sent one at a time through slits in a diffraction grating. Every single time, the same rule holds. Without a way to know the path, interference appears. With a way to know the path, it disappears. The rule is not about size. It is about information. To describe this mathematically, physicists use something called a wave function. It is not a physical wave moving through space like a sound wave or a wave on water. It is a mathematical object that encodes the probability of finding a particle at any given location, and it evolves smoothly and predictably according to an equation written down by Erwin Schrödinger in 1926. Before a measurement, an electron heading toward the double slit barrier is described by a wave function that has passed through both slits simultaneously, spreading out and interfering with itself, exactly like the water wave. Only when a measurement forces a definite outcome does the wave function collapse into a single, sharp answer. The electron is here, and nowhere else. This collapse is where the real trouble begins. The equation that governs how the wave function evolves is completely deterministic. Give it a starting state, and it will tell you exactly how that state changes in the future, with no randomness at all. But the moment a measurement happens, that smooth evolution appears to stop, and the wave function jumps unpredictably to one specific outcome, with a probability set by the wave function itself, but with no way to know in advance which outcome will actually occur. Two completely different kinds of physics seem to be operating in the same theory: smooth and deterministic when nobody is measuring, abrupt and probabilistic the instant a measurement happens. Physicists call this the measurement problem, and it has never been fully solved. It is not a matter of missing data or imprecise equipment. The mathematics of quantum theory works extraordinarily well, more precisely tested than almost any other theory in the history of science, correctly predicting the outcomes of countless experiments to many decimal places. What remains unresolved is the interpretation, the question of what is physically happening during that transition from spread-out possibility to single definite outcome, and what exactly counts as a measurement in the first place. This is the point where Erwin Schrödinger, one of the founders of the theory, tried to make the absurdity impossible to ignore. In 1935, he proposed a thought experiment, never actually performed, meant purely to expose a problem with taking the mathematics to literally. Imagine sealing a cat inside a closed box, along with a small amount of a radioactive substance, a Geiger counter, a vial of poison, and a hammer rigged to break the vial if the counter detects a decay event. Over the course of an hour, there is exactly a 50% chance that one atom of the radioactive substance decays. If it decays, the counter trips, the hammer falls, the vial breaks, and the cat dies. If it does not decay, the cat lives. Radioactive decay is a genuinely quantum process, governed by the same wave function mathematics as the electron in the double-slit experiment. Before anyone opens the box and checks, the decaying atom exists, according to the equations, in a superposition, a combination of having decayed and not having decayed at the same time, with equal weight given to each possibility. But the atom is now coupled to the counter, which is coupled to the hammer, which is coupled to the vial, which is coupled to the cat. If quantum superposition can apply to an atom, and if there is nothing in the mathematics that says superposition has to stop at some particular size, then by the same logic, the entire chain, and the cat along with it, should also end up in a superposition, simultaneously alive and dead, until someone opens the box and looks. Schrödinger did not intend this as a serious claim, that cats can be both alive and dead. He intended it as a challenge, somewhere between a single radioactive atom and a full-grown cat. Our intuition insists that the fuzziness of quantum superposition must give way to the ordinary certainty of classical reality. A cat is either alive or it is dead, long before anyone opens the box. But the equations of quantum mechanics, taken at face value and without any additional assumption about where measurement happens, give no indication of exactly where or why that transition should occur. The thought experiment does not answer the question. It sharpens it for decades. The The dominant response to this puzzle was what is now called the Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg in the 1920s. The Copenhagen view treats the wave function as a description of our knowledge about a system, not a physical object in its own right, and it draws a practical line between the microscopic quantum world, where superposition and probability rule, and the macroscopic classical world of measuring devices, cats, and human observers, where definite outcomes always apply. Measurement, in this view, is simply the process by which a quantum system interacts with a classical apparatus, and that interaction is what forces the wave function to collapse. The trouble with the Copenhagen interpretation is that it never precisely defines where the line between quantum and classical actually sits. A measuring device is, after all, made of atoms, and atoms obey quantum mechanics. There is nothing in the fundamental equations that singles out a Geiger counter, or a human eye, or a brain, as special or exempt from quantum rules. Bohr's answer was essentially pragmatic. Treat the measuring apparatus as classical because it works, and do not ask what is happening underneath. For many working physicists, running experiments and building technology, that pragmatism was, and still is, entirely sufficient. But for physicists interested in what is actually happening at the deepest level of reality, it left a gap that has never been closed. That gap becomes even harder to ignore once you scale the thought experiment up, push the boundary further than Schrödinger's cat, and ask what happens if the entity doing the observing is not a Geiger counter but a person. And what happens if a second person is watching the first person from outside? This is exactly the escalation that the physicist Eugene Wigner proposed in 1961, in a scenario now known as Wigner's friend. Picture a colleague, call her the friend, sealed inside a laboratory with a quantum system prepared in a superposition, similar to the radioactive atom in Schrödinger's setup. The friend performs a measurement on the system using a proper measuring device and gets a definite result. As far as the friend is concerned, the superposition has collapsed. She saw a single outcome, and there is no more uncertainty from her point of view now. Consider Wigner himself, standing outside the sealed laboratory. He has no access to the result of the friend's measurement. He knows only that a laboratory containing a quantum system, a measuring device, and a friend is sitting there, evolving according to the smooth, deterministic Schrödinger equation, exactly as it would if no collapse had happened at all. From Wigner's external perspective, the entire laboratory, including his friend's brain and her memory of the measurement she just performed, exists in a superposition of every possible outcome, undetermined until Wigner opens the door and asks his friend what she saw. So here is the uncomfortable question at the heart of the thought experiment. Did the wave function actually collapse the moment the friend made her measurement, or did it only collapse later, when Wigner learned the result? Both descriptions are internally consistent. Both use the same equations correctly, but they describe two different realities for the same physical situation. One where a definite outcome exists inside the lab from the friend's perspective, and one where the entire lab remains in an undetermined superposition from Wigner's perspective, right up until the moment information crosses the threshold of the door. For a long time, Wigner's friend was treated purely as a thought experiment, a philosophical exercise, rather than something that could actually be tested. That changed starting around 2016, when physicists began proposing, and eventually performing, real laboratory versions of the scenario using photons as tiny stand-ins for the friend's entire laboratory. In these experiments, an observation performed on one photon, playing the role of the friend's measurement, could later be shown, through a clever combination of measurements on entangled partner photons, to still be in a superposition from the perspective of a second, outside observer, playing the role of Wigner. The results, published by multiple independent research groups between roughly 2019 and 2023, are consistent with the unsettling reading of the thought experiment. Under certain assumptions about the nature of measurement and the existence of a single, observer-independent reality, the experiments produce statistical correlations that violate what should be possible if both the friend and Wigner shared one objective, agreed-upon fact about what happened inside the lab, at least one of several deeply held assumptions about how reality works has to give way. Either there is no single, universal fact about what any given measurement outcome was, independent of who is asking, or the free choice of what to measure is somehow not truly free, or influences can travel between separated systems in ways that appear to violate locality. None of the available options are comfortable ones for physicists who would like to believe in a single, shared, objective, external world. If the measurement problem were only about the present moment, about whether looking at something changes it right now, it would already be strange enough. But quantum mechanics has one more layer to add, one that seems, on the surface, to threaten the ordinary flow of cause and effect. It comes from an idea first proposed by the physicist John Wheeler in 1978, called the delayed choice experiment. Wheeler's proposal took the double-slit experiment and added a twist. What if you let a particle pass through the double-slit barrier so that it is already, in some sense, on its way toward the detector, and only then, after the particle has already passed through the slits, decide whether to measure which path it took? If deciding to check the path information after the fact still destroys the interference pattern, then it looks as though a choice made now can reach backward and determine how the particle behaved earlier, when it was still passing through the slits. This is not just a thought experiment anymore. Versions of it have been built and tested in laboratories many times since the 1980s, most famously in a series of experiments conducted by a French research team led by Ailing Aspect and later refined by numerous groups worldwide, including a particularly clean version reported in 2007 using single photons and fast optical switches capable of making a random decision after each photon had already entered the apparatus. Every time, the result matches Wheeler's prediction. Whether interference shows up depends on a choice that, from the point of view of an observer watching the clock, is made after the particle has already traveled most of its path. The most striking version of this idea is called the delayed choice quantum eraser, first demonstrated experimentally in 1999 by a research group led by Yoonho Kim, working with colleagues including Yunhua Shi. In this setup, a photon passes through a double slit and then, instead of hitting a detector directly, is sent through a special crystal that splits it into two entangled partner photons. One partner, called the signal photon, travels toward a detector that can, in principle, record an interference pattern. The other partner, called the idler photon, is sent along a separate path where experimenters can choose, using beam splitters and mirrors, whether or not to erase the which path information it carries. Here is the crucial part. The idler photon is deliberately routed along a longer path, so that it arrives at its own detector after the signal photon has already been recorded. And yet, when researchers go back afterward and sort the signal photon detections according to what was later done to their idler partners, whether the path information was erased or preserved, they find something remarkable. The signal photons whose idler partners had their path information erased do show an interference pattern. When grouped together after the fact, even though the signal photon was already detected before that choice was made, the signal photons whose idler partners had their path information preserved show no interference at all, forming two simple clusters. Instead, it is tempting to describe this as time travel, as though a decision made later reached back and changed what already happened. But that description does not survive close scrutiny, and it is worth being precise about what is and is not actually going on, because this is one of the most commonly misunderstood results in all of physics. No individual signal photon detection ever changes. The raw, unsorted data collected at the signal detector looks exactly the same, a simple, featureless blur with no interference pattern visible, regardless of what is later done to the idler photons. The interference pattern only appears after the fact, once the data has been split into two subsets based on the later measurement of the idler photon, and combined with information sent at ordinary speeds no faster than light, from the idler detector back to wherever the analysis is being done. Nothing is erased in the past. Nothing physically changes about a photon that has already been recorded. What changes is which subset of an already fixed, already collected pile of data reveals a pattern. Once you know how to sort it, this distinction matters enormously, because it means the delayed choice quantum eraser does not violate causality, and it does not allow any kind of usable signal to be sent backward in time. No information can be extracted from the signal photon detector alone that tells you, in advance, what choice will later be made about the idler photon. The strangeness is real, but it lives entirely within the correlations between entangled particles, correlations that only become visible once information from both sides of the experiment is brought together, and that combination can never happen faster than light allows. Still, the fact that a measurement choice made well after a photon was detected can determine, retroactively and statistically, whether that detection belongs to an interference pattern or not, is one of the clearest demonstrations that quantum entities do not carry fixed, pre-existing properties the way classical particles are assumed to. What a photon appears to have done depends on the entire experimental context, including parts of that context that have not happened yet at the moment the photon arrives. Entangled photons keep showing up in these experiments for a reason. Entanglement is arguably the strangest and most thoroughly tested phenomenon in all of quantum mechanics, and it deserves a closer look on its own terms, separate from the measurement problem, even though the two are deeply connected. When two particles are entangled, their properties become linked in a way that has no counterpart in classical physics. Suppose a source produces a pair of photons whose combined spin, or polarization, must add up to a fixed total value. The way two ice skaters pushing off from each other must have equal and opposite momentum. Before either photon is measured, quantum mechanics does not assign either one a definite polarization. Both exist in a shared superposition, correlated with each other, but individually undetermined. Send one photon to a laboratory on one side of a city and its entangled partner to a laboratory on the other side, and the moment someone measures the polarization of the first photon, getting some definite result, the second photon's polarization becomes instantly determined too correlated with the first, no matter how far apart the two laboratories. Albert Einstein found this deeply troubling. In a paper published in 1935, written together with Boris Podolsky and Nathan Rosen, he argued that this instantaneous correlation, which he famously described as spooky action at a distance, meant that quantum mechanics must be an incomplete theory. Einstein's intuition, shaped by decades of work on relativity, was that nothing physical should be able to influence something else faster than light can travel between them. His preferred explanation was that the particles must actually carry hidden, predetermined properties all along, fixed at the moment they were created, and that quantum mechanics simply failed to describe those hidden variables. The apparent randomness of quantum measurements, in this view, was not fundamental randomness at all, but a reflection of our ignorance of some deeper, more complete underlying theory. The same way that the apparent randomness of a coin flip is really just a reflection of our ignorance of its exact initial spin and air currents for almost 30 years. This remained a philosophical disagreement with no clear way to test it experimentally, since both quantum mechanics and a hidden variable theory could, in principle, predict the same statistical correlations between entangled particles. That changed in 1964, when the physicist John Stuart Bell found a way to turn the philosophical dispute into a testable mathematical inequality. Bell showed that any theory based on local hidden variables, meaning any theory where particles carry predetermined properties and where no influence can travel between them faster than light, must obey a specific statistical limit on how strongly the measurement outcomes of entangled particles can be correlated. Quantum mechanics, on the other hand, predicts that under the right conditions, those correlations can exceed that limit. This turned Einstein's philosophical objection into an experiment that could actually be run in a laboratory, and comparing the predicted numbers would settle the matter empirically rather than by argument alone. Starting in the 1970s and continuing through a landmark series of experiments performed by Albert Einstein and his colleagues in the early 1980s, physicists began measuring the correlations between entangled photon pairs with increasing precision. The results consistently violated Bell's inequality, matching the predictions of quantum mechanics and ruling out any theory based on local hidden variables. Skeptics pointed out, reasonably, that early versions of these experiments contained loopholes, small gaps in the experimental design that could, in principle, allow a local hidden variable theory to still explain the results through some overlooked technicality, such as inefficient detectors that missed too many photon pairs, or measurement settings that were not chosen quickly enough or randomly enough to rule out the possibility that the particles somehow knew in advance what would be measured. Over the following decades, these loopholes were closed one by one, through improvements in detector efficiency, through using rapidly switching random number generators to choose measurement settings, and through separating the two measurement stations by large enough distances that no signal traveling at the speed of light could connect them in time. By 2015, several independent research groups, including teams in the Netherlands, the United States, and Austria, had performed loophole-free Bell tests, closing essentially every remaining gap simultaneously. The violation of Bell's inequality held up every time this body of work was recognized with the Nobel Prize in Physics in 2022, awarded jointly to Erwin Schrödinger, John Glaser, and Anton Zeilinger for their experimental work, demonstrating violations of Bell's inequality and pioneering the field of quantum information science that grew out of it. A conclusion physicists have been forced to accept is genuinely radical. Nature does not behave like a system of particles carrying fixed, predetermined properties that simply reveal themselves upon measurement. At least one of two deeply intuitive assumptions has to be given up. Either locality, the idea that distant objects cannot influence each other faster than light allows, or realism, the idea that particles possess definite properties independent of whether or not they are being measured. Most physicists, following the standard interpretation of quantum mechanics, give up realism, accepting that particles genuinely do not have definite properties until measured, and that the correlations between entangled particles reflect something about the fundamentally holistic, non-separable nature of quantum systems, rather than any kind of faster-than-light signaling. Is worth being precise here as well, because entanglement is often misreported as allowing instant communication, and it does not. Although the correlation between measurement outcomes appears the instant both measurements are made, no usable information can actually be sent this way. The result of a measurement on one entangled particle looks completely random to the person making it, until it is compared, through an ordinary, light-speed limited communication channel, with the result of the measurement on the other particle. Only then does the correlation become apparent. There is no way to use entanglement alone to send a message, encode a choice, or transmit any information faster than light. A fact formally proven and known as the no communication theorem. What entanglement reveals is not a loophole in relativity, but something deeper and stranger about the structure of reality itself. A kind of connectedness between particles that exists prior to and independent of the ordinary notions of space and separation that classical physics assumes. Faced with all of this, that the equations behave deterministically until a measurement happens, that measurement outcomes depend on choices made even after the fact, and that entangled particles are correlated in ways no local hidden variable theory can explain. Physicists have developed several competing frameworks that try to make sense of what is actually happening. None of them is universally accepted. Each one solves part of the puzzle while introducing new difficulties of its own. The most radical of these is the many worlds interpretation. First proposed by the physicist Hugh Everett in 1957, Everett's idea was disarmingly simple in principle, even though its consequences are enormous. What if the wave function never actually collapses at all? What if the smooth, deterministic Schrödinger equation is the whole story, all the time, with no exceptions and no special role for measurement? Under this view, when the friend in Wigner's thought experiment measures a quantum system in superposition, the universe does not select one outcome and discard the rest. Instead, the entire universe, including the friend, the measuring device, and everything else entangled with the outcome, splits into separate branches, one branch for each possible outcome, all of them equally real, all of them coexisting, and simply no longer able to interact with or influence one another in the many worlds view. Schrödinger's cat truly is both alive and dead, just not in the same branch of reality. One version of the observer opens the box and finds a living cat. Another, equally real version, in a separate branch that split off from the same starting point, opens the box and finds a dead cat. Neither version is aware of the other, because the branches, once split, no longer interact. Wigner's friend paradox resolves cleanly in this picture too, since there is no genuine disagreement about what is real, only different branches of a much larger reality, each internally consistent, each containing its own definite outcome. That appeal of the many worlds interpretation is that it requires no new physics, no collapse mechanism, and no vague, undefined line between quantum and classical. It simply takes the existing equations at face value. The cost is a staggering multiplication of reality, with new branches splitting off from every quantum event, everywhere in the universe, constantly. An idea that many physicists find philosophically extravagant, even if it cannot be ruled out by any experiment so far devised, since by construction, every branch is causally cut off from every other one. A very different approach is the de Broglie theory, sometimes called pilot wave theory, first sketched out by Louis de Broglie in the 1920s and developed into a complete framework by David Bohm in 1952. This theory restores something closer to Einstein's original intuition. It proposes that particles do have definite positions at all times. They are never actually spread out or undetermined, but that their motion is guided by a real, physical wave, the pilot wave, which spans all of space and is shaped by the same wave function equation used in standard quantum mechanics. What looks like probabilistic randomness in ordinary quantum mechanics is, in the pilot wave picture, simply our ignorance of the particle's exact starting position, similar in spirit to Einstein's hidden variables idea, except that the guiding wave itself is explicitly not, meaning it can be influenced instantaneously across arbitrary distances. which is exactly the price the theory pays to remain consistent with the experimentally confirmed violations of Bell's inequality. Pilot wave theory reproduces every experimental prediction of standard quantum mechanics exactly, which is part of what makes it difficult to test against the alternatives. Its main drawback, from the perspective of many physicists, is that it requires this built-in non-locality as a fundamental, unavoidable feature of nature, uncomfortably at odds with the spirit, though not the letter, of relativity, and it has proven mathematically difficult to extend cleanly into a fully relativistic, field-theoretic form compatible with particle creation and annihilation, processes that are central to modern particle physics. A third family of approaches, known as objective collapse theories, takes yet another route. Rather than denying that collapse happens, as many worlds does, or explaining it away as revealed hidden information, as pilot wave theory does, these theories propose that collapse is a real physical process, governed by its own precise mathematical rules, that happens spontaneously and randomly to every particle, extremely rarely for a single isolated particle, but with overwhelming likelihood for any large collection of particles bound together, such as a measuring device or a cat. One well-known version, developed by Giancarlo Garardi, Alberto Rimini, and Tullio Weber in 1986, adds a tiny, built-in probability that any given particle will spontaneously collapse into a localized state at any moment. A probability far too small to notice for a single particle over the lifetime of the universe, but one that scales up rapidly with the number of particles involved. Since if any one particle in a large object collapses, it drags the whole entangled object with it. A related idea, explored by the physicist Roger Penrose, suggests that the collapse threshold might be set not by an arbitrary added rule but by gravity itself, proposing that a quantum superposition becomes physically unstable and collapses once the difference in space-time curvature between its possible outcomes reaches a certain critical scale, an idea that directly connects the measurement problem to unresolved questions in quantum gravity. What makes objective collapse theories especially interesting is that, unlike many worlds or pilot wave theory, they make predictions that differ, even if only very slightly, from standard quantum mechanics, meaning they are, at least in principle, experimentally distinguishable. If collapse is a real physical process with its own rate and its own trigger, then sufficiently careful experiments looking for tiny deviations from perfect quantum superposition, especially in larger and larger objects, should eventually be able to detect it, or rule it out. Alongside these interpretations sits a crucial piece of physics called decoherence, developed largely through the work of Wojciech, Zurek, and others beginning in the 1970s and 80s. Decoherence does not, by itself, resolve the measurement problem or say which interpretation is correct, but it explains something equally important, which is why the everyday world looks so reliably classical, even though it is built entirely out of quantum particles. Any quantum system that interacts with its environment, with stray air molecules, with photons of light, with the countless particles making up a measuring device, rapidly becomes entangled with that environment, and the interference effects that make superposition detectable get spread out and diluted across all of those extra particles so quickly and so thoroughly that they become, for all practical purposes, impossible to observe again. A cat is never truly isolated from its environment the way a single electron in a vacuum chamber can be. And decoherence explains why cats always appear either alive or dead, never in a detectable superposition of both, within an almost immeasurably short span of time, regardless of which deeper interpretation of quantum mechanics turns out to be correct. Zurek extended this idea further with a concept called quantum Darwinism, which describes how definite, classical-seeming facts about the world emerge and spread when a quantum system interacts with its environment. Information about certain preferred properties, called pointer states, tends to get copied redundantly into many different parts of the environment, into countless photons bouncing off an object. For instance, any observer who intercepts even a small fragment of that environment, a few photons reaching an eye, can recover the same information as any other observer intercepting a different fragment. This redundant copying is what gives rise to the sense of a single, shared, objective classical reality that many independent observers can agree on, even though, underneath it all, the fundamental description remains fully quantum mechanical. There is one more interpretation worth mentioning, because it takes the observer-dependent strangeness seen in the Wigner's friend experiments and embraces it directly, rather than trying to explain it away. Quantum Bayesianism, usually shortened to cubism, developed primarily by Christopher Fuchs in the 2000s, along with related relational approaches to quantum mechanics proposed by Carlo Rovelli beginning in the 1990s, argues that the wave function was never meant to describe an objective, observer-independent state of the world in the first place. Instead, it represents a specific agent's personal degree of belief about what outcomes they should expect, updated the moment that agent gains new information through a measurement. On this view, the disagreement between Wigner and his friend about whether the lab is in superposition is not a paradox at all, because there was never supposed to be one single, universal wave function that everyone must agree on. Each observer's wave function is their own accounting of their own information, and different observers, with different information, are simply entitled to different, equally valid descriptions. This approach dissolves several of the puzzles discussed so far, but it does so by giving up something many physicists are reluctant to abandon: the idea that physics describes a single, objective, mind-independent reality that exists the same way for everyone, whether or not anyone is looking at it. Critics argue that cubism trades a physics problem for a philosophy problem, replacing an unresolved question about collapse with an unresolved question about what an observer even is, and why physics, a field built on the premise of an external world existing independently of any particular mind, should give up that premise in the first place. None of this confusion is a recent development. The tension between these different ways of thinking about quantum mechanics goes back to the very people who built the theory, most famously in a series of debates between Albert Einstein and Niels Bohr that played out over more than 2 decades. Starting at the Solvay physics conferences of the late 1920s, Einstein, throughout his life, remained convinced that quantum mechanics, despite its predictive success, could not be the final, complete description of reality, and he spent years devising increasingly clever thought experiments designed to expose contradictions or loopholes in Bohr's Copenhagen interpretation. Bohr, in turn, methodically worked through each of Einstein's challenges, refining the interpretation and clarifying exactly what quantum mechanics did and did not claim, without ever fully satisfying Einstein's underlying objection that a fundamental physical theory should not have to rely on probability as anything more than a temporary stand-in for missing information. A very different approach is the de Broglie theory, sometimes called pilot wave theory, first sketched out by Louis de Broglie in the 1920s and developed into a complete framework by David Bohm in 1952. This theory restores something closer to Einstein's original intuition. It proposes that particles do have definite positions at all times. They are never actually spread out or undetermined, but that their motion is guided by a real, physical wave, the pilot wave, which spans all of space and is shaped by the same wave function equation used in standard quantum mechanics. What looks like probabilistic randomness in ordinary quantum mechanics is In the pilot wave picture, simply our ignorance of the particle's exact starting position, similar in spirit to Einstein's hidden variables idea, except that the guiding wave itself is explicitly not, meaning it can be influenced instantaneously across arbitrary distances, which is exactly the price the theory pays to remain consistent with the experimentally confirmed violations of Bell's inequality. Pilot wave theory reproduces every experimental prediction of standard quantum mechanics exactly, which is part of what makes it difficult to test against the alternatives. Its main drawback, from the perspective of many physicists, is that it requires this built-in non-locality as a fundamental, unavoidable feature of nature, uncomfortably at odds with the spirit, though not the letter, of relativity, and it has proven mathematically difficult to extend cleanly into a fully relativistic, field-theoretic form compatible with particle creation and annihilation, processes that are central to modern particle physics. A third family of approaches, known as objective collapse theories, takes yet another route. Rather than denying that collapse happens, as many worlds does, or explaining it away as revealed hidden information, as pilot wave theory does, these theories propose that collapse is a real physical process, governed by its own precise mathematical rules, that happens spontaneously and randomly to every particle, extremely rarely for a single isolated particle, but with overwhelming likelihood for any large collection of particles bound together, such as a measuring device or a cat. One well-known version, developed by Giancarlo Garardi, Alberto Rimini, and Tullio Weber in 1986, adds a tiny, built-in probability that any given particle will spontaneously collapse into a localized state at any moment, a probability far too small to notice for a single particle over the lifetime of the universe, but one that scales up rapidly with the number of particles involved. Since if any one particle in a large object collapses, it drags the whole entangled object with it. A related idea, explored by the physicist Roger Penrose, suggests that the collapse threshold might be set not by an arbitrary added rule but by gravity itself, proposing that a quantum superposition becomes physically unstable and collapses once the difference in space-time curvature between its possible outcomes reaches a certain critical scale, an idea that directly connects the measurement problem to unresolved questions in quantum gravity. What makes objective collapse theories especially interesting is that, unlike many worlds or pilot wave theory, they make predictions that differ, even if only very slightly, from standard quantum mechanics, meaning they are, at least in principle, experimentally distinguishable. If collapse is a real physical process with its own rate and its own trigger, then sufficiently careful experiments looking for tiny deviations from perfect quantum superposition, especially in larger and larger objects, should eventually be able to detect it, or rule it out. Alongside these interpretations sits a crucial piece of physics called decoherence, developed largely through the work of Wojciech, Zurek, and others beginning in the 1970s and 80s. Decoherence does not, by itself, resolve the measurement problem or say which interpretation is correct, but it explains something equally important, which is why the everyday world looks so reliably classical even though it is built entirely out of quantum particles. Any quantum system that interacts with its environment, with stray air molecules, with photons of light, with the countless particles making up a measuring device, rapidly becomes entangled with that environment, and the interference effects that make superposition detectable get spread out and diluted across all of those extra particles so quickly and so thoroughly that they become, for all practical purposes, impossible to observe again. A cat is never truly isolated from its environment the way a single electron in a vacuum chamber can be. and decoherence explains why cats always appear either alive or dead, never in a detectable superposition of both, within an almost immeasurably short span of time. Regardless of which deeper interpretation of quantum mechanics turns out to be correct, Schrödinger extended this idea further with a concept called quantum Darwinism, which describes how definite, classical-seeming facts about the world emerge and spread when a quantum system interacts with its environment. Information about certain preferred properties, called pointer states, tends to get copied redundantly into many different parts of the environment, into countless photons bouncing off an object. For instance, any observer who intercepts even a small fragment of that environment, a few photons reaching an eye, can recover the same information as any other observer intercepting a different fragment. This redundant copying is what gives rise to the sense of a single, shared, objective classical reality that many independent observers can agree on, even though, underneath it all, the fundamental description remains fully quantum mechanical. There is one more interpretation worth mentioning, because it takes the observer-dependent strangeness seen in the Wigner's friend experiments and embraces it directly, rather than trying to explain it away. Quantum Bayesianism, usually shortened to cubism, developed primarily by Christopher Fuchs in the 2000s, along with related relational approaches to quantum mechanics proposed by Carlo Rovelli beginning in the 1990s, argues that the wave function was never meant to describe an objective, observer-independent state of the world in the first place. Instead, it represents a specific agent's personal degree of belief about what outcomes they should expect, updated the moment that agent gains new information through a measurement. On this view, the disagreement between Wigner and his friend about whether the lab is in superposition is not a paradox at all, because there was never supposed to be one single, universal wave function that everyone must agree on. Each observer's wave function is their own accounting of their own information, and different observers, with different information, are simply entitled to different, equally valid descriptions. This approach dissolves several of the puzzles discussed so far, but it does so by giving up something many physicists are reluctant to abandon: the idea that physics describes a single, objective, mind-independent reality that exists the same way for everyone, whether or not anyone is looking at it. Critics argue that cubism trades a physics problem for a philosophy problem, replacing an unresolved question about collapse with an unresolved question about what an observer even is, and why physics, a field built on the premise of an external world existing independently of any particular mind, should give up that premise in the first place. None of this confusion is a recent development. The tension between these different ways of thinking about quantum mechanics goes back to the very people who built the theory, most famously in a series of debates between Albert Einstein and Niels Bohr that played out over more than 2 decades. Starting at the Solvay physics conferences of the late 1920s, Einstein, throughout his life, remained convinced that quantum mechanics, despite its predictive success, could not be the final, complete description of reality, and he spent years devising increasingly clever thought experiments designed to expose contradictions or loopholes in Bohr's Copenhagen interpretation. Bohr, in turn, methodically worked through each of Einstein's challenges, refining the interpretation and clarifying exactly what quantum mechanics did and did not claim, without ever fully satisfying Einstein's underlying objection that a fundamental physical theory should not have to rely on probability as anything more than a temporary stand-in for missing information. Neither man lived to see Bell's theorem tested in the laboratory. Einstein died in 1955, Bohr in 1962, both more than a decade before Ailing aspects experiments provided the first strong, empirical evidence bearing directly on their disagreement. It is one of the striking footnotes of 20th century physics that a philosophical dispute conducted largely through thought experiments and private correspondence was eventually settled, decades later, by hard experimental data, and that the data came down, in its essentials, on Bohr's side, against Einstein's intuition that reality must be locally real and fully determined even when nobody is measuring it. Whether Einstein would have found the many worlds interpretation, or pilot wave theory, or objective collapse models more palatable than the strict Copenhagen picture he originally objected to, is impossible to know. But it is worth remembering that even the very physicist who did more than perhaps anyone else to build quantum theory in its early years, through his explanation of the photoelectric effect and his foundational work on wave-particle duality, remained unconvinced for the rest of his life that it told the whole story. If the different interpretations mostly agree on the mathematics and only disagree on what that mathematics means, one natural way forward is to look for places where they might eventually make different, testable predictions, particularly around the question of exactly how large or how massive an object can be while still showing genuine quantum superposition. This has become one of the most active experimental frontiers in the field over the past 2 decades. The current record holders for the largest objects shown to exhibit wave-like interference are large organic molecules, including compounds built from more than 2,000 atoms, sent through diffraction gratings in ultra-high vacuum chambers by research groups including one led by Marcus Arndt in Vienna, in experiments extending the same basic double-slit logic first demonstrated with electrons nearly a century earlier. Each molecule, despite being large enough to contain thousands of protons, neutrons, and electrons, still produces the telltale interference pattern when its path is not measured, and still loses that pattern the moment which path information becomes available. Exactly as the theory predicts, a separate and rapidly advancing approach uses tiny mechanical objects, mirrors or vibrating membranes only a few micrometers across but still containing trillions of atoms, cooled down to temperatures just above absolute zero using laser cooling techniques, in an effort to place genuinely macroscopic, human visible objects into quantum superposition states. Researchers in this field, including groups working with levitated nanoparticles trapped by laser light in a vacuum, have succeeded in cooling such objects down to their quantum mechanical ground state and demonstrating quantum behavior, including superposition and entanglement between mechanical oscillators, in experiments reported through the 2010s and 2020s. The long-term goal of this research is to push the boundary of confirmed quantum behavior further and further toward the macroscopic, human-sized scale, both to test the predictions of objective collapse theories, which predict that superposition should become physically impossible to sustain past a certain mass and size threshold, and simply to see how far the strange rules of the double-slit experiment actually extend. A related class of experiments tests something called the Leggett-Garg inequality, proposed by Anthony Leggett and Anupam Garg in 1985 as a kind of temporal counterpart to Bell's inequality. Rather than asking whether distant particles can have definite properties independent of measurement, the Leggett-Garg inequality asks whether a single system can be assumed to have a definite, continuous history over time, even when it is not being measured, an assumption the authors called macroscopic realism. Experiments testing this inequality, performed with superconducting circuits and other systems capable of showing quantum behavior at unusually large scales, have found violations consistent with quantum mechanics and inconsistent with macroscopic realism, reinforcing the conclusion that quantum systems genuinely do not possess fixed, continuous properties between measurements, not just at the level of individual particles but at scales approaching the everyday world. None of this remains purely academic. The same superposition and entanglement that make the measurement problem so difficult to resolve philosophically are also the working ingredients of an entire emerging technology, quantum computing. A classical computer bit can only be a 0 or a 1. A quantum bit, or qubit, built from a trapped ion, a superconducting circuit, or a single photon, can exist in a superposition of both 0 and 1 simultaneously, and multiple qubits can be entangled together so that the total number of states the system can represent grows exponentially with each additional qubit added. A quantum computer with just 300 qubits, all mutually entangled, could in principle represent more simultaneous states than there are atoms in the entire observable universe. Not because it stores that many numbers individually, but because the mathematics of superposition allows certain calculations to explore an enormous space of possibilities simultaneously, before a final measurement collapses the system down to one answer. In October of 2019, a team at Google reported a milestone often called quantum supremacy or quantum advantage, in which a 53-qubit superconducting processor named Sycamore performed a specific, carefully chosen calculation in about 200 seconds that the team estimated would take the most powerful classical supercomputer at the time on the order of 10,000 years to complete. A claim later disputed and narrowed by competing research groups using improved classical algorithms, but one that nonetheless marked a genuine turning point in demonstrating that quantum superposition and entanglement can be harnessed to outperform classical computation for at least some carefully constructed problems. Since then, competing efforts from companies, including IBM, and research groups in China led by Guianwei Pan, have continued to push the frontier of qubit count, error correction, and computational advantage, all of it built directly on the same strange foundations explored in this discussion: superposition, entanglement, and the delicate, easily disturbed nature of a quantum state before it is measured. Quantum weirdness is not confined to isolated laboratory setups either. Over the past 2 decades, a field called quantum biology has accumulated evidence that some of these effects may play a functional role inside living organisms. Photosynthesis, the process by which plants and certain bacteria convert sunlight into chemical energy, appears in some organisms to rely on a phenomenon closely related to superposition, allowing energy absorbed by a light-harvesting pigment to explore multiple possible paths toward a reaction center simultaneously, finding the most efficient route with an effectiveness that classical, particle-like energy transfer alone struggles to explain. A finding first reported through detailed spectroscopy experiments beginning around 2007. Separately, some migratory birds, including European robins, appear to sense the Earth's magnetic field using a light-sensitive protein in their eyes called cryptochrome, through a mechanism that several research groups believe depends on quantum entanglement between a pair of electrons generated by light absorption, a hypothesis known as the radical pair mechanism, still actively investigated and debated as of the mid-2020s. These findings remain an active and sometimes contested area of research, but they suggest that the strange rules governing electrons at a double-slit barrier may not be confined to sterile laboratory equipment, and may, in specific and delicately balanced circumstances, leave a functional fingerprint on the biological world as well. There is another layer of strangeness worth understanding, closely related to entanglement but distinct from it, called quantum contextuality. In classical physics, an object is assumed to have definite properties that exist independently of how or whether you choose to measure them. An object has a definite position and a definite momentum whether or not anyone checks. In 1967, the mathematicians Simon Kochen and Ernst Specker building on earlier work by John Bell, proved a theorem showing that quantum mechanics cannot be explained by any theory in which particles carry fixed, predetermined values for all of their measurable properties, independent of the specific combination of other measurements being performed alongside them. In other words, the outcome you get when measuring one property of a quantum system can depend on which other compatible properties you happen to be measuring at the same time, even though those other measurements do not disturb the system in any obvious physical way. This is called contextuality, and unlike Bell's theorem, which concerns correlations between separated particles, the Kochen-Specker theorem applies even to a single particle, showing that the strangeness of quantum mechanics is not just about distant correlations, but about the very notion of a property having one fixed, context-independent value at all. Experimental tests of contextuality, performed with trapped ions and photons over the past 2 decades, have consistently confirmed the quantum mechanical predictions and ruled out the classical context-independent alternative. A related and often underappreciated quantum effect is called the quantum Zeno effect, named after the ancient Greek philosopher Zeno of Ilia, who argued that an arrow in flight, examined at any single frozen instant, appears motionless, and therefore motion itself must be an illusion. In quantum mechanics, something analogous turns out to be literally true and experimentally confirmed. If an unstable quantum system, one that would normally evolve or decay over time, is measured frequently enough, in rapid succession, each measurement has a tendency to reset the system back toward its original state, effectively freezing its evolution. First proposed, theoretically, in 1977 by George Sudarshan and Badian, and confirmed experimentally in 1990 with trapped beryllium ions by a team including Wigner. The quantum Zeno effect demonstrates, in a very direct and measurable way, that the simple act of frequent measurement genuinely changes the physical behavior of a quantum system, not just our knowledge of it, reinforcing the idea that measurement in quantum mechanics is not a passive act of observation but an active physical intervention with real, testable consequences. These effects raise a natural question. If a full, strong measurement forces a definite outcome and destroys superposition entirely, what happens with a partial, gentle measurement? One that extracts only a small amount of path information without fully destroying the interference pattern. This question has also been answered experimentally through a technique called weak measurement, developed theoretically by Yakia Aharonov, David Albert, and Lev Vaidman in 1988 and first realized in the laboratory in the early 2000s. A weak measurement interacts so gently with a quantum system that it barely disturbs it, extracting only a small, statistically noisy hint about which path a particle took, at the cost of only partially reducing the visibility of the resulting interference pattern rather than eliminating it outright. Experiments performed with single photons passing through a double-slit setup, using weak measurement techniques to trace out something resembling an average trajectory for the photons, while still preserving a faint interference pattern, were reported by a research group led by Ephraim Steinberg in 2011. The results showed a smooth, continuous trade-off between how much path information is extracted and how much interference survives, exactly matching the predictions of quantum mechanics, and demonstrating that the transition between wave-like and particle-like behavior is not a simple all-or-nothing switch, but a graded, continuous relationship governed precisely by how much information about the particle's path has entered the surrounding environment. Given how central the word observer is to popular descriptions of these experiments, it is worth directly addressing a common misconception, because it has caused genuine confusion for decades. Early in the history of quantum mechanics, a few physicists, most notably John von Neumann in his 1932 mathematical formulation of the theory, and later Eugene Wigner himself in some of his writings from the 1960s, speculated that consciousness, the subjective awareness of a human mind, might be what ultimately causes wave function collapse, since von Neumann's analysis showed that you could push the boundary between quantum system and classical measuring device arbitrarily far, from the particle to the detector, to the recording equipment, to the scientist's eye, to the scientist's brain, without ever finding an obvious, non-arbitrary place within the physical chain where collapse must occur. Other than the final step of conscious perception itself, this idea, however, is not supported by later experimental evidence, and is not the standard or accepted view among physicists working in the field today, including Wigner himself, who moved away from it later in his career. The interference pattern in the double-slit experiment disappears whenever which path information becomes physically recorded, anywhere in the environment. In a detector, in a stray photon, in a single entangled particle, regardless of whether any conscious being ever looks at that recorded information. Dicoherence, discussed earlier, explains this cleanly and without any reference to minds or consciousness at all, showing that the loss of interference is simply a consequence of the quantum system becoming entangled with a large, complex environment, which happens automatically and mechanically the instant that entanglement occurs. Whether or not a human being or any observer with a mind is anywhere nearby, a fully automated laboratory with no human present produces exactly the same loss of interference the instant its detectors record which path information, confirmed by numerous experiments run under precisely these unattended conditions. The persistence of the word observer in popular science writing is largely a historical relic of the theory's early terminology, not a genuine requirement for consciousness or awareness anywhere in the physical process. And correcting this misconception is one of the more important services good science communication can provide, since the mystical, consciousness-centered version of the story, while dramatic, is simply not what the evidence supports. None of the interpretations discussed so far have been confirmed or ruled out by experiment, and that unresolved status connects to an even bigger open problem in physics: the search for a theory of quantum gravity. General relativity, Einstein's theory of gravity, published in 1915, describes gravity not as a force but as the curvature of space-time itself, caused by the presence of mass and energy, and it has passed every experimental test thrown at it for more than a century. From the bending of starlight around the sun to the direct detection of gravitational waves from colliding black holes, first observed in 2015 by the LIGO detectors, quantum mechanics, meanwhile, has passed every experimental test thrown at it as well, describing the behavior of particles and fields with extraordinary precision. The trouble is that these two enormously successful theories are built on fundamentally incompatible mathematical foundations, and nobody has yet found a fully consistent way to combine them into a single theory that works in every regime, particularly in extreme environments where both gravity and quantum effects should matter simultaneously, such as the interior of a black hole or the first fraction of a second after the beginning of the universe. This is not a purely abstract concern, disconnected from the measurement problem discussed throughout this discussion. Roger Penrose's proposal that gravity itself might be the physical trigger for wave function collapse, mentioned earlier as one version of objective collapse theory, is a direct attempt to bridge these two unresolved problems, suggesting that the reason large objects cannot sustain quantum superposition is fundamentally gravitational, tied to the fact that two different mass distributions, corresponding to two different branches of a superposition, would curve spacetime in two subtly different ways, and that spacetime itself cannot indefinitely sustain that kind of ambiguity. Testing this idea directly is extraordinarily difficult, since the predicted collapse timescale for anything smaller than roughly 10 to the negative 14 kilograms, an almost inconceivably tiny mass by everyday standards, but a genuinely large one by the standards of a single particle, is far too slow to distinguish from ordinary environmental decoherence using current technology, though proposed experiments involving levitated nanoparticles isolated to an extraordinary degree from their environment, discussed by researchers including Angelo Bassi and collaborators, aim to close that gap over the coming decade. Separate but related puzzle sits at the boundary of quantum mechanics and gravity as well, known as the black hole information paradox, first identified by Stephen Hawking in 1976. Hawking showed that black holes are not perfectly black after all, but slowly emit a faint form of thermal radiation, now called Hawking radiation, caused by quantum effects occurring right at the boundary of the black hole, its event horizon. Over an enormous span of time, this radiation causes a black hole to gradually lose mass and eventually evaporate away entirely. The trouble is that Hawking's original calculation showed this radiation to be purely thermal and random, carrying no detailed information about whatever originally fell into the black hole, whether it was a star, a spaceship, or a pile of encyclopedias. But one of the most fundamental principles of quantum mechanics, closely related to the deterministic evolution of the wave function discussed earlier, is that information about a physical system's exact state should never be truly destroyed, only ever transformed or scrambled beyond practical recovery. If a black hole can completely evaporate away while genuinely destroying all information about what fell into it, quantum mechanics and general relativity appear to give flatly contradictory answers about whether that information still exists somewhere in the universe. This paradox has driven a huge amount of theoretical work over the past several decades, including major contributions from physicists such as Leonard Susskind, Juan Maldacena, and Don Page, and it remains, as of the mid-2020s, not fully and universally agreed upon, although a series of theoretical breakthroughs beginning around 2019, involving mathematical objects called quantum extremal surfaces and a calculation known as the Page curve, have provided a strong argument, within certain simplified but physically motivated models, that information is indeed preserved and gradually leaks out encoded within the correlations of the Hawking radiation itself, rather than being destroyed, though translating this result into a fully general, rigorously proven statement about real, physical black holes remains an active area of ongoing research. The black hole information paradox and the measurement problem are not the same puzzle, but they share a common root. Both arise from asking exactly how and where the smooth, information-preserving evolution described by quantum mechanics meets a process, whether it is a measurement or an evaporating event horizon that appears, at least on the surface, to produce a definite, seemingly irreversible outcome. Entanglement has also been pushed well beyond simple pairs of particles. In 1989, the physicists Daniel Greenberger, Michael Horn, and Anton Zeilinger described a way to entangle 3 or more particles together simultaneously, in states now called GHC states after their initials, which produce correlations even stranger than ordinary 2-particle entanglement, strange enough that a single, carefully chosen measurement on a GHC state can, in principle, rule out local hidden variable theories without needing to gather statistics over many repeated trials at all, unlike Bell's original inequality, which requires averaging over a large number of measurements to reveal its violation. Experimental demonstrations of GHC states and their extensions 2, 4, 6, and eventually many more entangled particles have been achieved by research groups over the following decades, most notably by teams working with Anton Zeilinger in Vienna and John Wei Pan in China, pushing the practical boundary of controllable, multi-particle entanglement steadily higher and providing an increasingly rich testbed for probing exactly how far the strangeness of quantum correlations extends as more particles are added to the mix. This work has not remained confined to laboratory tabletops either. In June of 2017, a Chinese research satellite named Messius, launched the previous year specifically for this purpose, successfully distributed entangled photon pairs between ground stations separated by more than 1,200 kilometers, using one photon of each entangled pair beamed down to each of 2 distant observatories, and confirmed a violation of Bell's inequality across that enormous distance, far beyond what is achievable using entangled photons sent through optical fiber on the ground, where losses over long distances make the signal too weak to detect reliably. This satellite-based approach has since been used to demonstrate intercontinental quantum key distribution, a form of communication that uses the physical properties of entangled particles to detect any attempted eavesdropping between ground stations in China and Austria, laying early groundwork for what researchers describe as a future quantum internet, a network capable of distributing entanglement and quantum information across global distances, with applications extending beyond secure communication into distributed quantum computing and enhanced measurement techniques based on entangled sensors. Researchers have also worked to close remaining loopholes in Bell tests using increasingly exotic methods of choosing measurement settings, since one lingering, if extremely remote, possibility is that the supposedly random choices of what to measure at each detector are not actually free or random at all, but were somehow secretly correlated with the particles being measured, all the way back to some common cause in the shared past, a scenario sometimes called the freedom of choice loophole. To address this, physicists have used light from distant astronomical sources, including stars and even quasars, billions of light years away, to help determine the random measurement settings used in Bell tests, reasoning that any conspiracy linking those measurement choices to the particles in the laboratory would have had to have been set up before that ancient starlight even began its journey toward Earth. Experiments using this approach, including a large-scale project called the Cosmic Bell Test conducted in 2017 using light from stars, roughly 600 years old, and a later version in 2018 using light from quasars billions of years old, have continued to confirm violations of Bell's inequality, pushing the time frame over which any conceivable hidden conspiracy would have had to operate back further and further into the deep cosmic past, without finding any sign that quantum mechanics is wrong taken together. This enormous and still growing body of experimental work, spanning nearly a full century from the earliest double-slit measurements with electrons to satellite-based entanglement, distribution and loophole-free Bell tests using ancient starlight, has left the mathematics of quantum mechanics essentially unchallenged. Every prediction tested so far has held up. What remains genuinely unresolved is not whether the equations work. They clearly do, better than almost any other physical theory humans have ever produced. But what those equations are actually describing about the underlying nature of reality, and specifically what physically happens, if anything, during the transition that ordinary language calls a measurement. So, where does the research actually stand right now? Heading into the second half of the 2020s, several distinct experimental programs are actively underway, each chipping away at a different piece of the puzzle. The push toward larger and larger superposition states continues, with groups working on levitated nanoparticles trapped by laser light aiming to place objects containing billions of atoms into clean, verifiable superposition states, isolated as thoroughly as possible from the decohering effects of stray heat, air molecules, and vibration, in an effort to test directly whether Penrose's gravity-based collapse proposal or other objective collapse models predict a real, measurable deviation from standard quantum mechanics at some specific, calculable mass and size threshold, or whether superposition really can be sustained indefinitely at any scale, limited only by how well an experiment can be isolated from its environment. Parallel efforts are underway to refine and extend the experimental tests of the Wigner's friend scenario, moving beyond the simplified versions using single photons as proxies for an entire observer toward setups involving larger, more complex quantum systems intended to more faithfully represent what an actual, conscious or measuring observer would experience, in an effort to determine more precisely which of the deeply held assumptions, a single objective shared reality, free and independent choice of measurement settings, or strict locality, must ultimately be abandoned, and under exactly what conditions quantum computing hardware continues to scale up as well, with major efforts at Google, IBM, and other companies and research institutions racing to increase both the number of qubits and, just as importantly, the fidelity and error correction capabilities of those qubits, since a large number of noisy, error-prone qubits is far less useful than a smaller number of extremely stable, well-protected ones, achieving what is often called fault-tolerant quantum computation, where errors can be detected and corrected faster than they accumulate, remains one of the central engineering challenges in the field, and success would unlock the ability to run algorithms, such as certain approaches to simulating complex molecules for drug discovery and materials science, or breaking specific forms of cryptographic encryption currently considered secure against classical computers that are believed to be far beyond the reach of any classical machine. However powerful on the theoretical side, physicists working on quantum gravity continue to search for a mathematically consistent framework that unifies general relativity and quantum mechanics, pursuing several competing and not mutually exclusive research programs, including string theory, which proposes that fundamental particles are actually tiny vibrating strings existing in a higher dimensional space, loop quantum gravity, which proposes that spacetime itself is built from discrete, quantized units at an extremely small scale, and a more recent and increasingly influential line of research growing out of the black hole information paradox, exploring the idea that spacetime and gravity themselves might not be truly fundamental at all, but might instead emerge from the pattern of quantum entanglement between more basic underlying degrees of freedom, an idea sometimes summarized by researchers, including Mark van Romsdank, with the phrase that spacetime is built from entanglement, suggesting a deep and still not fully understood connection between the strange, seemingly delicate phenomenon of quantum entanglement discussed throughout this exploration, and the very geometric fabric of space and time itself. None of these research directions have yet produced a single, universally agreed upon answer to the measurement problem, and it is entirely possible that none of them will for a long time to come, if ever. It is worth being honest about that, rather than pretending a resolution is just around the corner. What has changed dramatically over the past several decades is not the theoretical picture so much as the experimental one, since ideas that were once purely philosophical, debated only through thought experiments and private letters between Einstein and Bohr, have become testable, measurable, and in many cases, definitively confirmed. even while the deeper question of what that confirmation actually means for the nature of reality remains as contested as ever. It is worth stepping back and asking why any of this should matter beyond the walls of a physics laboratory, since the practical, everyday world seems, on its surface, to run just fine on ordinary, classical rules. Chairs stay solid, cats are either alive or dead, and nobody has ever reported walking through two doors at once. Part of the answer is technological, since the same quantum principles at the heart of this discussion, superposition and entanglement, already underpin real, deployed technologies, from the lasers and transistors that make up ordinary electronics, which rely on quantum mechanical descriptions of how electrons behave inside solid materials, to the atomic clocks that keep GPS satellites synchronized precisely enough to pinpoint a location on Earth to within a few meters, to the earliest generation of genuinely useful quantum computers and quantum communication. Networks now beginning to move out of research laboratories and into limited real-world deployment. But there is a deeper reason this remains one of the most actively discussed open problems in all of physics, one that goes beyond any particular application. The measurement problem sits at the intersection of physics and some of the oldest questions in philosophy, about the nature of reality, the reliability of cause and effect, and what it even means for something to be real or true independent of anyone checking. Does the universe contain a single, definite, objective history, the same for every observer? Or does reality only become definite relative to a particular observer's frame of reference and accumulated information? As the Wigner's friend experiments seem to suggest, is the future genuinely open and undetermined until it happens, with quantum randomness representing a true, fundamental source of unpredictability baked into the laws of nature? Or is randomness, as pilot wave theory and objective collapse theories in their different ways suggest, ultimately explainable by some deeper, more complete underlying mechanism not yet discovered? Does asking these questions about determinism and randomness at the level of individual particles have any real bearing on larger, more familiar questions about human choice and free will, given that the human brain, like everything else, is built out of quantum particles? Even though decoherence overwhelmingly suggests that any quantum effects inside a warm, wet, noisy brain would be washed out far too quickly to influence the kind of large-scale, complex decision-making associated with conscious thought, a point argued forcefully by physicists, including Max Tegmark, in a widely cited 2000 paper calculating just how fast decoherence occurs inside neural tissue. These are not questions physics can settle by mathematics alone, since the equations of quantum mechanics work equally well no matter which interpretation you adopt, and choosing between many worlds, pilot wave theory, objective collapse, Copenhagen, or cubism is, at least for now, as much a matter of which philosophical costs a person is willing to accept as it is a matter of which experimental data has been collected. This is precisely what makes the measurement problem so unusual among open questions in physics. Most unsolved problems in physics are, at their core, waiting on better data, a more powerful telescope, a higher energy particle collider, a more sensitive detector. The measurement problem is different, since an enormous and rapidly growing body of extraordinarily precise experimental data already exists, confirming the predictions of quantum mechanics again and again with essentially no exceptions. And yet that data still leaves room for multiple, mutually incompatible pictures of what is actually happening underneath, each internally consistent, each compatible with every experiment performed so far. And physicists actively disagree, sometimes passionately, about which picture, if any, is correct. One further result deserves mention. because it pushes the strangeness of superposition into territory that sounds, at first, almost like a magic trick, even though it has been demonstrated in real laboratories. In 1993, the physicists Avshalom Elitzur and Lev Feynman proposed a thought experiment, now known as interaction-free measurement, or, more colorfully, the Elitzur-Feynman bomb tester. Imagine a batch of bombs so sensitive that a single photon striking their trigger will set them off. And suppose that some of these bombs are duds, containing no explosive at all, with a trigger mechanism that simply lets a photon pass through untouched. The challenge is to find a way to identify which bombs are live and which are duds, without ever actually detonating a live one, and, crucially, without directly touching or interacting with the bomb's trigger in a way that would obviously destroy it. If it happened to be lived, the solution relies on a device called an interferometer, a setup that splits a single photon's path into two routes using a half-silvered mirror, sends each route around a different arm of the apparatus, and then recombines them at the end. If both arms are left completely open, with nothing blocking either path, the two halves of the photon's wave function interfere with each other on recombination in a very specific, predictable way, always producing a result at one particular output port and never the other, a consequence of the wave nature of the photon exploring both paths simultaneously. Now place one of the bombs in one of the two arms of the interferometer. If the bomb is a dud, the photon passes through as though nothing were there, and the interference pattern remains undisturbed, producing the same predictable result as before. But if the bomb is live, its trigger mechanism effectively acts as a which path measurement, since a live bomb can only either explode if the photon happens to travel down that arm or fail to explode, revealing that the photon must have traveled down the other arm, and either outcome destroys the delicate interference that depended on the photon exploring both paths without a definite answer as to which one it took. Remarkably, quantum mechanics predicts, and later experiments beginning in 1994 confirmed, that there is a genuine, non-zero probability in the simplest version of the setup, exactly 1 in 4, of the photon triggering neither outcome expected from an undisturbed interference pattern, appearing instead at the previously impossible second output port, revealing with total certainty that a live bomb is present in one of the arms, even though the photon that carried this information can be shown by the specific path it took through the apparatus to have never actually traveled down the arm containing the live bomb at all. Information about the bomb's presence is obtained without the photon ever directly interacting with it, extracted instead from the way the mere possibility of interaction, present in the other, unexplored branch of the photon's superposition, altered the overall pattern of interference. Refined versions of this technique, developed through the following decades, using a rapid sequence of many weak interactions, rather than a single interferometer, have pushed the theoretical success rate for interaction-free detection arbitrarily close to certainty, and the underlying principle has since found genuine practical application, including in a widely cited 2004 experiment that used interaction-free measurement to image the shadow of an object using far fewer photons than would strike the object directly under classical imaging methods, demonstrating that the effect is not merely a laboratory curiosity but a real, exploitable resource with implications for extremely low light imaging, including potential applications in photography of light-sensitive biological samples that cannot tolerate significant illumination. John Wheeler, the same physicist who first proposed the delayed choice experiment discussed earlier, spent much of the later part of his career trying to draw out the broadest possible implications of results like these. Wheeler noticed a pattern running through interaction-free measurement. the delayed choice experiments, and the quantum eraser, all of them showing that what a quantum system appears to have done depends not on some fixed, pre-existing fact about its journey, but on the entire experimental arrangement, including choices made well after the system has already, in an ordinary sense, arrived. In a series of papers and lectures during the 1980s and 90s, Wheeler proposed a provocative framework he called the participatory universe, summarized in his frequently quoted phrase, "it from bit," suggesting that physical reality, at its most fundamental level, might be better understood not as made of matter and energy in the traditional sense, but as built from countless discrete, binary answers to yes or no questions. Questions posed, in effect, by measurement itself. Wheeler illustrated the idea with a game he called 20 questions with no answer fixed in advance, in which the person being questioned does not decide on a specific object at the start of the game, as in the ordinary version, but instead simply answers each question consistently with all the previous answers already given, so that the identity of the object only becomes fully determined by the final question asked, an intentional echo of the way a quantum system's history only becomes determined. In experiments like the delayed choice quantum eraser, once the full sequence of measurements has actually been carried out, Wheeler's participatory universe idea remains a minority position among physicists, more a philosophical proposal than a rigorously tested physical theory, and it should be understood as one physicist's attempt to find a unifying narrative across a genuinely bewildering collection of experimental results, rather than as an established scientific conclusion. But it is worth mentioning because it captures something real about why these experiments keep surprising people who encounter them for the first time. The intuitive picture most people carry around of a universe made of small, definite objects, quietly possessing fixed properties, waiting to be discovered by measurement the way a hidden object waits to be found in a game of hide and seek, is precisely the picture that a century of accumulating quantum experiments has steadily, carefully, and repeatedly dismantled, replaced by something considerably harder to visualize, in which the very notion of a definite property, a definite path, or a definite history only fully applies once the right kind of interaction has occurred, and remains genuinely open in every sense the mathematics can support. Until that interaction takes place, a useful historical footnote here belongs to the physicist Mauritius, who in 1953, decades before the Feynman bomb tester was proposed, pointed out a simpler version of the same basic idea, now known as the Renninger negative result experiment. Renninger noted that if a particle's wave function has spread out to cover two separate regions of space, and a detector placed in one of those regions fails to click, the absence of a detection event is itself a kind of measurement, since it instantly tells you, with complete certainty, that the particle must be located in the other region, causing the wave function to collapse there, even though no detector in that other region ever physically interacted with the particle at all. Renninger's simple observation that not detecting something can be just as physically meaningful, and just as capable of causing collapse as detecting it, anticipated by 4 decades the more elaborate and experimentally realized, interaction-free measurement schemes that followed, and it remains one of the clearest, simplest illustrations available of just how central the flow of information, rather than any direct physical disturbance, is to understanding what a measurement actually is in quantum mechanics. Pull all of these pieces together and a strange but coherent picture starts to take shape, even without settling on a single interpretation. A single electron, sent alone toward to open slits, behaves as though it explores both paths simultaneously, right up until information about its path becomes available anywhere in the universe, at which point it commits to one path or the other. Whether that information becomes available can, in carefully designed experiments, be decided after the particle has already arrived at its detector, without allowing any signal to travel backward in time, but revealing, once the full dataset is sorted, that the particle's behavior was never truly fixed, independent of the entire experimental context, including choices made after its arrival. Two particles, created together and then separated by any distance, however large, show correlations in their measurement, outcomes that cannot be explained by any theory in which each particle secretly carried a fixed, predetermined set of properties all along. A conclusion confirmed not just in ordinary laboratories, but using entangled photons beamed between satellites and ground stations, more than 1,000 kilometers apart, and using randomness drawn from starlight and quasar, light billions of years old, to rule out even the most exotic conceivable loopholes. And when the entity doing the measuring is not a simple detector but an entire laboratory, complete with a human colleague forming a genuine memory of a definite outcome, the question of whether that outcome is truly fixed, or only fixed relative to who is asking, has been shown, through direct experimental tests of the Wigner's friend scenario, to have no fully comfortable answer, forcing a choice between abandoning locality, abandoning free and independent measurement choices, or abandoning the assumption that a single, objective, observer-independent reality exists at all. None of the major interpretations built to explain this. Many worlds, with its constantly branching multiplicity of coexisting realities, pilot wave theory, with its hidden, definite particle positions guided by an invisible, instantaneously acting wave spanning all of space, objective collapse theories, with their proposal of a genuine, physically real, spontaneously occurring collapse process possibly tied to gravity itself, or the more radically observer-centered views like cubism, which give up the idea of a single shared reality altogether, have been ruled out by any experiment performed so far. Each one reproduces every confirmed prediction of standard quantum mechanics exactly, differing only in what story they tell about what is happening underneath the equations, and in some cases, differing in subtle, as yet untested predictions about exactly where and why quantum superposition should eventually give way to ordinary classical certainty as objects grow larger and more complex. This is precisely the situation that keeps drawing new generations of physicists into quantum foundations research, since it represents a genuinely rare case in modern physics of a problem that is not simply awaiting more precise measurement of an already well-understood quantity, but is instead awaiting either a genuinely new experimental result capable of distinguishing between fundamentally different pictures of reality, or a conceptual breakthrough capable of showing why one picture, previously considered merely a matter of taste, is actually required by logic or by some deeper physical principle not yet identified. The mathematics of quantum mechanics has remained essentially unchanged and completely unchallenged for nearly a full century, an extraordinary track record for any scientific theory. And yet the question of what that mathematics is actually telling us about the nature of the universe we live in remains as open now as it was when Einstein and Bohr first began arguing about it at the Solvay conferences nearly 100 years ago. So what, honestly, do scientists still not know? They do not know with certainty whether the universe truly branches into a constantly multiplying set of parallel realities every time a quantum measurement occurs, or whether there is only ever one reality, definite and singular, just one whose fundamental building blocks do not carry fixed properties the way classical intuition assumes. They do not know whether there is a genuine, physical collapse process built into the laws of nature, waiting to be discovered and precisely measured through experiments on increasingly large and well-isolated quantum systems, or whether the appearance of collapse is simply what decoherence looks like from the inside, with no additional physics required at all. They do not know how, or even whether, quantum mechanics and general relativity will eventually be unified into a single, complete theory, and they do not know whether solving that unification will also resolve the measurement problem, or whether the two puzzles, despite their apparent connections through ideas like gravitationally induced collapse and entanglement-built spacetime, will ultimately turn out to be separate problems requiring separate solutions. What they do know, and what nearly a century of steadily improving experiments has established beyond reasonable doubt, is that the classical, intuitive picture of a universe made of small, solid objects carrying fixed, well-defined properties at all times, waiting patiently to be discovered by measurement, is not how nature actually operates. Not at the scale of electrons and photons, and based on ongoing experiments pushing further into the macroscopic realm, quite possibly not at any scale. Up to and including cats, laboratories, and, though the case remains inconclusive and heavily debated, observers themselves, the experiments described throughout this discussion continue right now, in laboratories on every continent, using ever more sophisticated tools, colder temperatures, more isolated environments, and more cleverly designed tests, chasing a question that has remained essentially unchanged in its essentials since Schrödinger first proposed his thought experiment about a cat in 1935, even as the tools available to investigate it have grown almost unrecognizably more powerful. If you found this exploration of the deepest unresolved question in physics interesting, following along for more of the discoveries and experiments continuing to reshape our understanding of reality, and passing this along to anyone else who might find a universe without fixed, definite properties just as fascinating, helps keep this kind of careful, evidence-based exploration of genuinely open scientific questions going. Physics has, at various points in its history, resolved questions that once seemed permanently mysterious. The nature of heat, the structure of the atom, the origin of the elements forged inside stars, each one eventually yielding to careful experiment and better theory. The measurement problem may, someday, join that list, resolved by an experiment not yet designed, or a theoretical insight not yet had, or it may turn out that quantum mechanics, in refusing to fully resolve, is telling us something true and permanent about the limits of what a single, unified, observer-independent description of reality can ever capture, that the universe, examined closely enough, simply does not owe us the kind of definite, complete picture that classical physics trained us to expect. Either way, the question remains exactly where Einstein and Bohr left it in their debates nearly a century ago. Actively investigated, rigorously tested, and, for now, genuinely, productively unresolved, which is very likely why it continues to draw some of the sharpest minds in physics toward it, generation after generation, each one hoping to be the one who finally sees, clearly and completely, what is actually happening in that small, dark space between an electron leaving its source and a detector recording where it landed. Institutions across the world are currently devoted specifically to pursuing these open questions. Among them, the Institute for Quantum Optics and Quantum Information in Vienna, where much of the Bell test and Wigner's friend experimental work discussed throughout this exploration has been carried out. The QTech Research Center at Delft University of Technology in the Netherlands, which performed one of the first loophole-free Bell tests in 2015, a joint institute of the University of Colorado Boulder and the National Institute of Standards and Technology. known for precision experiments on trapped ions and atomic clocks that continue to test the boundaries of quantum behavior, and the Perimeter Institute for Theoretical Physics in Canada, home to much of the ongoing theoretical work connecting quantum information, entanglement, and the structure of space-time. None of these groups expect to settle the measurement problem within the next few years. What they do expect, based on the steady, incremental pace of progress over the last several decades, is that each new generation of more sensitive, more isolated, more precisely controlled experiments will continue narrowing the range of interpretations still compatible with the data, even if a final, universally accepted answer remains out of reach for now. It is a genuinely rare thing in science to have a question this fundamental about the basic nature of reality remain this actively, rigorously, and productively studied for this long, without either being resolved or being abandoned as unanswerable. The measurement problem has done neither. It has instead become one of the most carefully tested, most experimentally scrutinized open questions in the history of physics. A puzzle where the uncertainty is not a sign of neglect, but a sign of exactly how seriously and how precisely physicists have taken the challenge of finding out what is actually true.